Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 3 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is multivariate normal distribution. As we have discussed in the first lecture, the econometric relationships are not exact, but stochastic in nature, and that stochastic behavior we observe because of the presence of random error term or random disturbance term in the model. Obviously, for making inferences about the model, say for example, for the estimation of parameters or for testing the hypothesis regarding the parameters, we require to assume a proper probability distribution for the distribution of random error terms or random disturbances. In univariate, the normal distribution or Gaussian distribution plays a crucial role. The distribution is characterized by two parameters, its mean and its variance. And as you know, most of the distributions can be approximated by normal distribution successfully. Now, in econometrics, the errors or the disturbances are not univariate, but we get a random vector. So, obviously, we require a multivariate distribution as the distribution for disturbances, and a natural extension of normal distribution is the multivariate normal distribution. The multivariate normal distribution is characterized by the mean vector, the variances of different components. Not only that, it also involves the covariances or correlations between different components. So, it is characterized by the mean vector and variance covariance matrix. In fact, not only as the distribution of disturbances, but for approximating the distribution of many statistics also, we can use the multivariate normal distribution because of the multivariate central limit theorem. You can approximate the distribution of many statistics by the multivariate normal distribution. So, in this lecture, I am going to discuss some basic properties of the multivariate normal distribution, some of the results of multivariate normal distribution which we will require in the subsequent lectures. Of course, again for most of the results I will skip the proof. Of course, for some of the results I will give you the proof, but for most of the results I will not give you the proof. Now, before coming to the multivariate normal distribution, first we define the mean vector and variance covariance matrix of a random vector. So, suppose you have a p cross 1 random vector x, the order of x is p cross 1. So, we write x equal to x1, x2, xp transpose. The ith component of x is xi. Then the mean vector of x is defined as expectation of x equal to, say we write it equal to mu, where mu is again a p cross 1 vector with components mu 1, mu 2, mu p. So, for taking expectation of x, this random vector x, what we do? We take expectation of each of the components of x, say expectation of xi, which is equal to mu I, and then we arrange these mu i's in this vector form. So, you get expectation of x equal to mu. Then the variance covariance matrix of x is defined as, we take x minus mu transpose, and then we take expectation of each of the components of this matrix. Obviously, x minus mu is of order p cross 1 and its transpose is of order 1 cross p. So, ultimately x minus mu transpose is a matrix of order p cross p. And suppose we denote the expectation of x minus mu transpose by sigma, and we write sigma equal to sigma 1 1, sigma 1 2, so on sigma 1 p and so on sigma p 1, sigma p 2, sigma p p. So, this is a p cross p matrix. Here capital sigma has ijth element small sigma ij, where for I equal to j, sigma I is equal to expectation of xi minus mu I square. So, the ith diagonal element of capital sigma gives you the variance of xi, and for I not equal to j, the ijth element of capital sigma is equal to sigma ij, and sigma ij is equal to expectation of xi minus mu I xj minus mu j, which gives you the covariance between xi and xj. This capital sigma is a positive definite symmetric matrix. It is of course symmetric because the covariance between xi and xj is same as the covariance between xj and xi. So, sigma ij is equal to sigma ji. Then the correlation coefficient between xi and xj we denote it by say rho ij is equal to sigma ij, the covariance between xi and xj divided by the square root of sigma ii into sigma jj, that is the variance of xi into variance of xj. Now, we come to the multivariate normal distribution. Again, we consider a p cross 1 random vector x, then x is said to follow a p-variate normal distribution if its probability density function is of the form, say f x given mu sigma is equal to 1 upon 2 pi to the power p by 2, determinant of capital sigma to the power half, exponential minus half x minus mu transpose sigma inverse x minus mu, where x belongs to the p dimensional Euclidean space. Here you can easily verify that the expectation of x is equal to mu. So, mu gives you the mean vector of x, and expectation of x minus mu transpose is equal to sigma. So, capital sigma gives you the variance covariance matrix of x, and we denote it by x follows NP, means p-variate normal distribution with mean vector mu and variance covariance matrix sigma. Here again capital sigma is a positive definite symmetric matrix. Sigma ii gives you the variance of xi and sigma ij gives you the covariance between xi and xj. And just like the general case, you can define the correlation coefficient between xi and xj as rho ij equal to sigma ij divided by square root of sigma ii sigma jj. Actually, capital sigma is called the variance covariance matrix because its diagonal elements give you the variances of different components of x, and off diagonal elements give you the covariances between different components of x. Means sigma ij gives you the covariance between xi and xj. In particular, suppose you take sigma ij equal to sigma square for all I equal to j and 0 for all I not equal to j. Means all the components of x have the same variance sigma square and the covariances are equal to 0. So, different components of x are uncorrelated with each other. So, that capital sigma is a diagonal matrix with diagonal elements small sigma square. All the diagonal elements are equal to sigma square. All the off diagonal elements are 0. So, you can write it equal to sigma square IP. IP is the identity matrix of order P. Then for this particular case, f x given mu sigma square is equal to, you have 1 upon 2 pi to the power p by 2, then determinant of sigma is equal to sigma square IP determinant of this, which is equal to sigma to the power 2p. Then you have to take determinant of sigma to the power half. So, you get sigma to the power p here, exponential minus 1 upon 2 sigma square, because you have capital sigma inverse here, and capital sigma inverse is equal to 1 upon sigma square I p. So, ultimately you get minus 1 upon 2 sigma square x minus mu transpose x minus mu here. And you can easily verify that this is equal to product j equal to 1 to p 1 upon 2 pi to the power half sigma e to the power minus half x j minus mu j square. So, in this particular case, you can write the joint PDF of different components of x as the product of their marginal PDFs. Again, if z follows NP 0 IP, means mean vector is 0 and variance covariance matrix is IP. So, small sigma square is also equal to 1. Then PDF of z is, say we denote it by phi z equal to 1 upon 2 pi to the power p by 2 e to the power minus half z transpose z. So, just like the univariate standard normal distribution, this y z is the PDF of p variate standard normal distribution. If z follows NP 0 IP, then we say that z is a standard normal random vector, or its probability density function is p variate standard normal distribution. Again, you can easily derive the characteristic function of x, which is defined as expectation of e to the power I t transpose x, where t is a p cross 1 vector. So, the characteristic function of x, where x follows n p mu sigma, is given by psi t is equal to e to the power I t transpose mu minus half t transpose sigma t. So, this is the expression for the characteristic function of a p variate normal distribution having mean vector mu and variance covariance matrix sigma. Now, suppose x follows n p mu sigma and we define y equal to alpha plus a x. So, y is actually a linear transformation of x, where A is any m cross p matrix of rank m, m is less than or equal to p. Then the distribution of y is also multivariate normal distribution. Actually, the order of y is m cross 1. So, y follows n, m means m variate normal distribution with mean vector nu, where nu is equal to alpha plus a mu. You can easily verify that expectation of y is equal to alpha plus a times expectation of x, which is mu. So, nu is equal to alpha plus a mu, and the variance covariance matrix of y is omega, where omega is equal to a sigma a transpose. So, if you take this kind of linear transformation of x, then for this transformation y also follows a multivariate normal distribution. In fact, you can verify this result using this characteristic function also. Now, suppose P is an orthogonal matrix such that P sigma P transpose is an identity matrix, and we define Z equal to P x minus mu. Then Z follows a p variate normal distribution having mean vector 0 and variance covariance matrix I p. and its PDF is of the form phi z equal to 1 upon 2 pi to the power p by 2 e to the power minus half z transpose z. In fact, you can easily verify this result 3.3 using the result 3.2, because z is a linear transformation of x. So, the distribution of z is also a multivariate normal distribution, and its mean is, you simply take expectation of p x minus mu, which is equal to p expectation of mu is mu, expectation of x is mu minus mu, and then this is equal to 0. The variance covariance matrix of Z is P, the variance covariance matrix of X, which is sigma P transpose, and then P sigma P transpose is an identity matrix. So, if you take this transformation of X, then you get a standard normal or p variate standard normal distribution. Suppose we partition the p cross 1 random vector x into two parts, x 1 and x 2, where x 1 consists of the first q components of x. So, x 1 is equal to x 1 x 2 so on x q transpose, and this x 2 is consist of the remaining p minus q components of x. So, we have partitioned x into first q components and remaining p minus q components. Accordingly, we partition the mean vector also. Expectation of x is equal to mu, and we write it equal to mu 1 mu 2, where mu 1 has first q components of mu, and this mu 2 has remaining p minus q components of mu. Then the variance covariance matrix sigma is partitioned as sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2. Here you have q columns and then p minus q columns, then q rows, p minus q rows. So, actually expectation of x I minus mu I, x I minus mu I transpose is equal to sigma I for I equal to 1 2, means expectation of x 1 minus mu 1, x 1 minus mu 1 transpose gives you sigma 1 1. Similarly, for I equal to 2, expectation of x 2 minus mu 2, x 2 minus mu 2 transpose gives you sigma 2 2, and expectation of x 1 minus mu 1, x 2 minus mu 2 transpose gives you sigma 1 2, and sigma 2 1 is same as sigma 1 2 transpose, or sigma 1 2 is same as sigma 2 1 transpose. Then x 1 and x 2 are independently distributed if and only if sigma 1 2 is equal to 0. Actually, if you look at different elements of sigma 1 2, the different elements of sigma 1 2 give you the covariances between different elements of x 1 and x 2. Say 1/1th element of sigma 1 2 is the covariance between x 1, the first element of this x 1 is, the first element is x 1, and the first element of x 2 is x q plus 1. So, 1/1th element of sigma 1 2 is the covariance between x 1 and x q plus 1, and then x 1 and x 2 are independently distributed if and only if sigma 1 2 is equal to 0. Then if you derive the marginal distribution of x 2, the marginal distribution of x 2 is again multivariate normal distribution having p minus q components. It has mean vector mu 2, which is actually the expectation of x 2, and variance covariance matrix sigma 2 2. And then the conditional distribution of x 1 given x 2 is also multivariate normal distribution, and this has conditional mean vector expectation of x 1 given x 2 equal to mu 1 plus sigma 1 2 sigma 2 to inverse x 2 minus mu 2 equal to nu 1 say, and the variance covariance matrix of x 1 given x 2 is, so expectation of x 1 minus nu 1 x 1 minus nu 1 transpose given x 2 is equal to sigma 1 1 minus sigma 1 2 sigma 2 to inverse sigma 2 1. You can easily verify that when sigma 1 2 is equal to 0, then this part vanishes. So, the conditional expectation of x 1 given x 2 when sigma 1 2 is equal to 0 does not depend upon x 2, it is equal to mu 1, and the conditional variance is sigma 1 1 when sigma 1 2 is equal to 0. Actually, if you consider this equation as a regression of एक नजर रुक जाइए to give is the covariance between x1, the first element of this x1 is, the first element is x1 and the first element of x2 is x q plus 1. So, 1/1th element of sigma 1 2 is the covariance between x1 and x q plus 1, and then x1 and x2 are independently distributed if and only if sigma 1 2 is equal to 0. Then if you derive the marginal distribution of x2, the marginal distribution of x2 is again multivariate normal distribution having p minus q components. It has mean vector mu 2, which is actually the expectation of x2, and variance covariance matrix sigma 2 2. And then the conditional distribution of x1 given x2 is also multivariate normal distribution, and this has conditional mean vector expectation of x1 given x2 equal to mu 1 plus sigma 1 2 sigma 2 to inverse x2 minus mu 2 equal to nu 1 say, and the variance covariance matrix of x1 given x2 is, so expectation of x1 minus nu 1 x1 minus nu 1 transpose given x2 is equal to sigma 1 1 minus sigma 1 2 sigma 2 to inverse sigma 2 1. You can easily verify that when sigma 1 2 is equal to 0, then this part vanishes. So, the conditional expectation of x1 given x2 when sigma 1 2 is equal to 0 does not depend upon x2, it is equal to mu 1. Then if you derive the marginal distribution of x2, the marginal distribution of x2 is again multivariate normal distribution having p minus q components. It has mean vector mu 2, which is actually the expectation of x2, and variance covariance matrix sigma 2 2. Then we consider the conditional distribution of x1 given x2, which is also a multivariate normal distribution, and it has mean vector expectation of x1 given x2 equal to mu 1 plus sigma 1 2 sigma 2 to inverse x2 minus mu 2, and we write it equal to say nu 1. The conditional variance covariance matrix of x1 is expectation of x1 minus nu 1 x1 minus nu 1 transpose given x2 is equal to sigma 1 1 sigma 1 2 sigma 2 to inverse sigma 2 1. Again, you can easily verify that when sigma 1 2 is equal to 0, then this part of the mean vector vanishes, and expectation of x1 given x2 becomes mu 1, and the conditional variance covariance matrix becomes sigma 1 1, because for sigma 1 2 equal to 0, this part becomes 0. So, for sigma 1 2 equal to 0, the conditional variance covariance matrix of x 1 is simply the unconditional variance covariance matrix of x 1. Now, suppose Z follows normal distribution, p-variate normal distribution having mean vector 0 and identity variance covariance matrix, and M is an idempotent matrix. The rank of M is Q, and Q is less than or equal to P. Then Z transpose M Z follows a chi-square distribution having q degrees of freedoms. Now, we prove this result. In the last lecture, lecture 2, we discussed the result that if M is an idempotent matrix having rank q, then there exists an orthogonal matrix P such that P transpose M P is equal to lambda, and lambda is a diagonal matrix having elements 1, 1, 1, 0, 0, so on 0. So, if rank of M is q, then q elements are equal to 1 and remaining p minus q elements are equal to 0. In fact, if M is an idempotent matrix, then q of its eigenvalues are 1 and remaining p minus q eigenvalues are 0. And this matrix lambda, this diagonal matrix lambda is consist of the eigenvalues of M. Then you can write Z transpose M Z equal to Z transpose P, P transpose M, P, P transpose Z, because P is an orthogonal matrix. So, P, P transpose is an identity matrix. Then P transpose M P is equal to lambda. So, we write lambda here, and suppose V is equal to P transpose Z. So, here you get P and Z transpose P is equal to V transpose. So, you get V transpose lambda P, and V transpose lambda V is equal to summation j equal to 1 to q V j square, because the first q diagonal elements of lambda are 1 and remaining elements are equal to 0. So, V transpose lambda V is equal to summation j equal to 1 to q V j square. Again, if you consider the distribution of V, then V also follows a p-varied normal distribution. It has mean vector same as the mean vector of Z 0, and the variance covariance matrix is P transpose the variance covariance matrix of Z is I P P, and this is equal to P transpose P, which is I P. So, V follows N P 0 I P. So, V 1, V 2, V q are IID standard normal variates. So, this implies that summation j equal to 1 to q V j square follows a chi-square distribution with q degrees of freedoms. Now, we consider some results of matrix differentiation. So, we define Z equal to Z 1, Z 2, Z k transpose. So, actually Z is a k by 1 vector, and then we take del z or del over del z equal to del over del z 1, so on del over del z k transpose. Then del over del z A transpose Z is equal to A, where A is also a k by 1 vector. Actually, A transpose Z is equal to A 1 Z 1 plus A 2 Z 2 plus A k Z k. So, if you take del over del Z 1 A transpose Z, then this is equal to A 1 del over del Z 2 A transpose Z is equal to A 2, and so on. Then we arrange all these in a vector and this is equal to A. Similarly, you can obtain del over del z A z equal to A transpose. Then if A is a symmetric matrix, then del over del z Z transpose A z is equal to 2 A z. To verify this result, of course, I am not going to give you the details of the proof, but to verify this result, you just write Z transpose A z as summation I summation j A I j, where A I j is the ijth element of capital A, Z I Z j. And remember that A I j is equal to A j I, and then you differentiate it with respect to Z I, and then you can verify this result. If you differentiate 2 times, del 2 or del z transpose A z is equal to 2 A. Now, we consider some results which we will require in subsequent lectures. I will also prove all these results. So, result 3.9, which is also known as Stein's univariate lemma. Suppose Z is a standard normal variate. So, Z follows a normal distribution having mean 0 and variance 1. And then G is a function from R to R. G is absolutely continuous with derivative del over del z, Z z denoted by G dash z. And we also assume that expectation of mod G dash z is finite. So, expectation of mod G dash z exists, then expectation of z G z is equal to expectation of G dash z. So, for obtaining expectation of z G z, you simply take derivative of G z and obtain direct expectation of G dash z. Now, we prove this result. So, we denote the PDF of a standard normal distribution by phi z. Then we use the integration by parts, and we start with the right hand side of equation 3. So, the right hand side of equation 3 is expectation of G dash z, and expectation of G dash z is integral from minus infinity to plus infinity G dash z phi z dz. We multiply G dash z by the PDF of z, and then we integrate, and then we integrate by parts. So, you take phi z here, integrate G dash z with respect to z. So, you obtain G z, take limit from minus infinity to plus infinity, minus, then we integrate from minus infinity to plus infinity, you take integral of G dash z, which is G z, and then we differentiate phi z, which is phi dash z dz. Now, the first term phi z G z, limit of this from when z tends to minus infinity is 0, because phi z tends to 0 as z tends to minus infinity. Similarly, phi z tends to 0 when z tends to infinity. So, this first term is equal to 0. Then phi z is equal to 1 upon 2 pi to the power half e to the power minus half z square. And if we differentiate phi z with respect to z, we obtain phi dash z equal to minus 1 upon 2 pi to the power half z e to the power minus half z square. So, we substitute the value of phi dash z here. Actually, this is equal to minus z phi z. So, we write phi dash z equal to minus z phi z. So, you get plus sign here, integral from minus infinity to plus infinity z g z phi z d z. And this gives you expectation of z z z. So, hence we obtain the result. Now, we extend this result for the multivariate case. So, suppose z is equal to z 1 z 2 z k transpose and del z is del over del z equal to del over del z 1 so on del over del z k transpose. So, this result is also called the Stein's multivariate lemma. So, suppose z follows a k-variate standard normal distribution and g is a function mapping from R k to R. G is absolutely continuous and differentiable, and the derivative of z z with respect to z is denoted by del z g z. Then expectation of z g z is equal to expectation of del z g z. So, this is the multivariate extension of previous result, and now we prove this result. To prove this result, let us write z minus I equal to z 1, z 2, so on z I minus 1, z I plus 1, so on z k. So, to define z minus I, what we have done? We have removed the ith component z I from z. Then for some I and given z within bracket minus I, the function g z I z minus I is univariate, and since this is a univariate function for the given z I, so we can apply Stein's univariate lemma, that is the previous result. Also notice that z I and z within bracket minus I are independently distributed. So, we use the independence of z I and z minus I. So, you get expectation of del over del z I z I z minus I equal to, first we take expectation with respect to z I and then we take the expectation with respect to remaining components of z, that is z minus I, and then inside you have del over del z I g z I z minus I, then expectation z minus I. Here we apply Stein's univariate lemma. So, expectation of this term del over del z I g z I z minus I with respect to z I is same as the expectation of z I g z I z minus I with respect to z I. So, you get this expression here, and then you are taking expectation with respect to z I, and then outside you have expectation with respect to the remaining components of z, that is z minus I. So, finally, you obtain the expectation of z I g z, because g z I z minus I is same as g z, and then this result holds for all I. So, this is true for all I. Then we arrange all these results in the form of a vector, and finally, you obtain expectation del z g z is equal to expectation z g z. So, finally, you obtain this result. Now, suppose y follows a normal distribution having mean vector theta and variance covariance matrix sigma square I k. Then we have expectation of y minus theta g y is equal to sigma square expectation del y g y. So, now we are going to extend the previous result when the mean vector is not 0, but theta, and the variance covariance matrix is not identity, but it is sigma square I k. So, then we get this result. To prove this result, we take the transformation z equal to 1 upon sigma y minus theta. So, y has mean vector theta. So, z has mean vector 0. Again, y has variance covariance matrix sigma square I k. So, z has variance covariance matrix I k. So, z follows a k variate normal distribution with mean vector 0 and variance covariance matrix I k. And then we also observe that del over del z I is equal to del y I over del z I del over del y I, and del y I over del z I is equal to sigma. Now, notice that y I minus theta I is equal to sigma z I. So, del y I over del z I is equal to sigma. So, del over del z I is equal to sigma times del over del y I. Hence, expectation of y I minus theta I g y is equal to sigma times expectation of z I g sigma z plus theta. Y is equal to sigma z plus theta. And then expectation of this term is equal to sigma times del over del z I g sigma z plus theta, and then this is equal to sigma square times expectation del over del y I g y. So, finally, you obtain expectation of y minus theta g y is equal to sigma square expectation of del y g y. Now, we obtain some expectations which we will require in this course. Say, suppose x follows a multivariate normal distribution with mean vector mu and variance covariance matrix sigma. A and B are two p cross 1 vectors, and capital A is p cross p matrix which has the ijth element A I j. Then expectation of A transpose x is obviously equal to A transpose expectation of x, and expectation of x is equal to mu. So, you get A transpose mu. Further, if you define the quadratic form x transpose A x, then x transpose A x is equal to summation I equal to 1 to p, summation j equal to 1 to p, A I j x I x j. And suppose you have to obtain the expectation of this quadratic form. So, expectation of x transpose A x is equal to summation I summation j. A I j is a constant. So, you can take it outside the expectation sign and you get expectation of x I into x j. Further, expectation of x I into x j is equal to, you simply write x I equal to x I minus mu I plus mu I, and similarly you write x j equal to x j minus mu j plus mu j, and then you multiply these two. So, you got expectation of x I minus mu I into x j minus mu j plus mu I into mu j. Then you have the cross product term, say x I minus mu I into mu j plus x j minus mu j into mu I, and we take expectation of this. Then expectation of x I minus mu I into x j minus mu j is equal to sigma I j, the covariance between x I and x j, plus mu I into mu j. Then expectation of this term x I minus mu I is equal to 0. Similarly, expectation of x j minus mu j is also 0. So, you get sigma I j plus mu I mu j. Then expectation of x transpose A x is equal to summation over I summation over j A I j. We substitute the value of expectation of x I into x j. So, you get sigma I j plus mu I into mu j, and summation over I summation j A I j sigma I j. This is actually equal to trace of A sigma. You can easily verify it, just to multiply A and sigma and then you take trace, or you take sum of all the diagonal elements, and then summation I summation j A I j mu I mu j is the quadratic form mu transpose sigma mu. Or alternatively, you can also derive this expectation as you write x transpose A x equal to trace of A x x transpose. Actually, what is the order of x transpose A x? This is of order 1 cross p, p cross p, p cross 1. So, this is a scalar, and trace of a scalar is the same scalar. Further, trace of x transpose A x is equal to trace of A x x transpose. So, you have trace of A x x transpose, and then we write trace of A, we write x equal to x minus mu plus mu, and similarly we write x transpose as x minus mu plus mu transpose. So, you get trace of A x minus mu transpose plus mu transpose A mu, because you have trace of A mu, mu transpose is equal to mu transpose A mu, plus twice mu transpose A x minus mu, and then we take expectation of x transpose A x. Now, taking expectation of both sides, we get expectation of x transpose A x equal to trace of A expectation of x minus mu transpose plus mu transpose A mu is a constant. So, expectation of mu transpose A mu is equal to the same constant mu transpose A mu, and the third term is twice mu transpose A, then you take expectation of x minus mu, which is equal to 0. So, this last term vanishes. So, you obtain trace of A sigma, because expectation of x minus mu transpose is equal to sigma. So, you get trace of A sigma plus mu transpose A mu. Further, if you have two linear combinations, say A transpose x and B transpose x, then covariance of A transpose x, B transpose x is equal to expectation of A transpose x minus A transpose mu into B transpose x minus B transpose mu, and then we write A transpose x minus A transpose mu into B transpose x minus B transpose mu as A transpose x minus mu B transpose x minus mu. Now, the order of B transpose X minus mu is 1 cross 1. So, you can write it as B transpose X minus mu as X minus mu transpose B. So, you get A transpose, then expectation of X minus mu transpose B, and expectation of X minus mu transpose is equal to sigma. So, you get A transpose sigma B. Further, you can easily verify that if capital sigma is equal to, say, sigma square times I p. So, all the diagonal elements of capital sigma are sigma square and all off diagonal elements are equal to 0. Then covariance between A transpose X, B transpose X is equal to sigma square A transpose B. And if these two vectors are orthogonal to each other, that is A transpose B is equal to 0, then covariance between A transpose X and B transpose X is equal to 0. So, these two linear functions of X, A transpose X and B transpose X are uncorrelated, provided sigma is this matrix and A and B are orthogonal to each other. Now, before finishing this lecture, I am also going to introduce this chronicle product. We will require this chronicle product in subsequent lectures. So, suppose A is M cross N matrix having ijth element A I j and B is P cross Q matrix having k lth elements, say B k L. Then we define A chronicle product P as A 1 1. So, we take the first element of A, we multiply it by the matrix B, or you can say we multiply each element of B by A 1 1. Then we take A 1 2 B and so on A 1 n B and so on A m 1 B, A m 2 B, so on A m n B. So, ultimately you obtain a matrix of order M p cross N q. M is the number of rows of A, P is the number of rows of B. So, corresponding to each row of A in chronicle product, you have P rows corresponding to B, and finally, you obtain M into P rows in A chronicle product B, and similarly, you obtain N into Q columns in this chronicle product. Now, we consider some results of chronicle product. Say, suppose you have 4 matrices A, B, C and D, then A chronicle product B into C chronicle product D is equal to A C chronicle product B D. Of course, we assume that the simple product of matrices A and C is possible and the simple product of matrices B and D is possible. Then A chronicle product B transpose is equal to A transpose chronicle product B transpose. And then from the first result we observe that for the square matrices A and B, so suppose A is of order M cross M and B is of order P cross P, and both of these matrices are non-singular, then A inverse chronicle product B inverse is into A chronicle product P is equal to A inverse A canonical product, B inverse B, A inverse A is IM, B inverse B is IP. Then IM canonical product IP is equal to IMP. So, this is an identity matrix, and this gives you the result that A canonical product B inverse is equal to A canonical product B. So, in this lecture we have discussed the multivariate normal distribution and its various properties. We have also discussed some of the results related with multivariate normal distribution, and we will require all these results in subsequent lectures. So, here I am going to stop. Thank you.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So, if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So, that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So, we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So, when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.